morning. This is Math 20-2, Chapter 2, Lesson 2 on deductive reasoning. So before we start deductive reasoning, we need to review what inductive reasoning was that we did last week. So inductive reasoning is a conclusion that you draw based on prior experience, based on observations, patterns that you've discovered. It does not mean that it's true in all cases. It just means it's true for all the cases that you've examined up to this point. There could be a counterexample that you just couldn't think about or that you haven't discovered yet. So we can't use inductive reasoning to prove a conjecture. I can't prove a statement is true or false beyond a shadow by inductive reasoning, or I guess prove it's true. Proving it false, I can find a counterexample. But I can't prove that conjecture is true in every case by using inductive reasoning, because all I'm doing is just generating a whole bunch of examples and not providing that counterexample that might exist somewhere. So in order to make or to prove a conjecture, I need logical reasoning. I need deductive reasoning. So for example, Susie drops off a film at the quick 1 hour photo. They advertise that your film is developed in 1 hour or there's no charge. So Susie drops the film off at 10 a.m. and it's not ready until 11:15. Well, what can she deduce from this information? What is her conclusion? The conclusion is that Susie will receive the developing for no charge. Because it took more than an hour to develop her film, you can make the deduction that she will not have to pay for it. It's like a pizza place saying that they will have your pizza to you within half an hour or it's free of charge. If it's more than half an hour, the conclusion that you can draw from that is that you're going to get it for free. So deductive reasoning or logical reasoning is the process of using true statements to arrive at a conclusion. So if we look at the next two class examples, write a conclusion that can be deduced from each pair of statements. Every whole number is an integer and 6 is a whole number. So what conclusion can we put if we take these two statements and put them together? Well, we have that a whole number is an integer and 6 is a whole number, so we can conclude that 6 is an integer. The next example, water freezes below 0 degrees Celsius. The temperature is minus 15 degrees Celsius. What is our conclusion? The conclusion would be that the water is frozen. Okay. If we can take a conjecture, a statement, and we can prove it using deductive reasoning, we no longer have to call it a conjecture, we can call it a theorem. A theorem is a statement that can be proved using logical or deductive reasoning. And that's what we're going to work on for the remainder of this lesson. It's not doing these proofs. There are many ways that you can approach them. I'm only showing you one way of approaching them. So don't think that that's the only way that you can solve these questions. There's other logical, algebraic ways that we could solve these questions and still come up with these conclusions. So in class example number 4 of lesson 1, we used inductive reasoning to write a conjecture that said that the sum of 3 consecutive integers was divisible by 3. That was the one where we had 5 plus 6 plus 7 equals 18, 11 plus 12 plus 13 equals 36, and so on. So the sum was always a number that was divisible by 3. Actually, it was 3 times this middle number. So if we were to prove that the sum of 3 consecutive integers is a multiple of 3, what we would need to do is we would need to use variables rather than using numbers. Because if I use numbers, I'd have to go through all the possible numbers that I could ever think of, positive, negative, rational, irrational. Whereas if I use variables, that variable could stand for anything. So it makes my job a little bit easier. So if I start off with three numbers, 5, 6, and 7. So what I can do is I can let these three numbers then represent variables. So if I started with my middle number, because we know my middle number had something to do with that total and with that divisibility. So I'm going to let it be equal to n. And then what I would do is I would let the 5 and the 7, I would write them in terms of that n. In other words, how do I go from 6 to 7? I add 1. So I would do the same thing with my n. I would add 1. How would I go from 6 to 5? I would subtract 1. So what I've done is I've taken my 5, 6, 7 and I've written them as variables where instead of this being 5, 6, 7, this could now be 16, 17, and 15. Or it could be 115, 116, 117. It could be 715, 716, 717. These numbers no longer matter because the n values replace that. So here's my three consecutive numbers, n minus 1, n, and n plus 1. If I was to add them together, this is my statement that I would get. So if I collect my like terms, all I've done is I've bunched my like terms together. I put all the n's together and then all the constants together. I have 3 n's, and my negative 1 and my positive 1 cancel each other out. 3n is divisible by 3, which means it must be a multiple of 3. So the sum of any 3 consecutive integers is a multiple of 3. I've just actually proven that without using inductive reasoning, because remember, n could be anything. N could now be a negative number, it could be a decimal, it could be a fraction. It's not limited by just being the 5, 6, 7, or whatever examples that I pull out of the air. That's how we do logical reasoning. So let's look at class example B. Complete the chart and make a conjecture using inductive reasoning. So I'm going to do the first test case. Choose a number less than 10. I'm going to pick 5. Then I'm going to follow the steps. Add 7. Well, that gives me 12. Multiply by 2. That would give me 24. Subtract the original number, so 24 minus 5 is 19. 19, now I subtract 2, and I get 17. And then I subtract the original number, and I get 12. So what I want you to do is I want you to press pause, and I want you to pick 2 more numbers. The condition is it has to be a number less than 10. So pick 2 more numbers, and then complete the chart. So I'll pick 2 more numbers randomly. If I pick 1, add 7, I get 8, multiplied by 2 is 16, subtract 1, I get 15, subtract 2, I get 13, subtract the original number, and I get 12. And I could even go into the negatives. If I took negative 4, add 7, and I get 3, multiplied by 2, and I get 6. This is the tricky one. Subtract by the original number. 6 minus negative 4 gives me 10. Subtract 2 gives me 8. Subtract the original number. So 8 minus negative 4, I get 12. So what is my conjecture? My conjecture would be that no matter what number is chosen, the final answer is 12. matter what number is chosen, the final answer is 12. This is simply a conjecture at this point in time. It is not a proof. It is not a rule or anything like that because I have not used deductive reasoning. All I did is I picked examples. There could be a counter example out there that I haven't even thought of. So, if we were to use deductive reasoning, instead what I would do is I would let x represent my original number. So, choose a number less than 10. That's my x. Okay, the only condition is x has to be less than 10. Add 7. So if I take x and then I add 7, the next part is to multiply by 2. So if I take my x plus 7 and I multiply it by 2, I get 2x plus 14. Then I'm told to take this and subtract the original number, which was x. So if I have a 2x minus x, I get x plus 14. Now I subtract 2. So 14 minus 2 gives me 12, and I get x plus 12. And then the last step was to subtract the original number, which was x. X minus x is 0. I have 0 x's left. And that gives me that 12. So what we've done is we've proved that whatever the original number chosen, the final answer would always be equal to 12. Now the question is, did this number have to be less than 10? Could I have picked a number a bit greater than 10? I picked x. What is x equal to? X could be anything. Positive, negative, rational. It could be a fraction, it could be a decimal. So, does the original number have to be less than 10? No. It could be anything. So we'll just say it could be any rational number. Actually, it could be any real number, not even rational. So to continue on with the rest of our examples, we have statements that concern odd and even numbers. So when we're dealing with odd and even numbers, we're going to use the following notation. 2 times n, or it could be 2 times x, 2 times p, 2 times y, 2 times my variable will represent an even number. Because any number I multiply by 2 is going to be an even number. 2 times 3 is 6, 2 times 7 is 14, 2 times 37 is 74. I always get an even number. 2n minus 1 or 2n plus 1 will represent odd numbers. Because if I have an even number, such as 6, to get an odd number, add 1, gives me 7. Subtract 1, gives me 5. So this is the type of notation we're going to use to designate our even numbers and our odd numbers. So in class example number 4, it says, explain why 2 times n, where n is a natural number, can be used to denote every even number. Well, all even numbers are divisible by 2. 2 times n is a multiple of 2. Doing very well writing today. Which means it's divisible by 2. So then why could I use 2n minus 1 to denote every odd number? Well, every odd number is 1 less, or it could be 1 more. If I did 2n plus 1. So every odd number is 1 less than every even number. So if 2n represents the even number, 2n minus 1 would be the odd number because it would be 1 before that. So if we use that to look at class example number 5, it says, when 2 odd numbers are added, their sums are always even. Use inductive reasoning or 3 cases to state that this is true. So if I pick 2 odd numbers, any 2 odd numbers, 1 plus 13 equals 14. That's an even number. So I want you to press pause, and I want you to pick 2 more. I went 3 plus 33, I get 36. If I pick 57 and 63, I get 120. All of those numbers are even, and all of the ones that you put together should be even. When we are talking about odd numbers, we are talking about natural numbers, so they have to be whole numbers, and they have to be greater than 0. So now, if we were to prove this statement, this did not prove the statement because I did not think of every possible example, and there could be a counterexample. So, if I was to prove this statement, 2 odd numbers, the sum of 2 odd numbers is an even number. I'm going to let my 2 odd numbers be 2n minus 1 and 2m minus 1. I use different variables because these 2 numbers would be different. So the sum of these 2 numbers I'm trying to prove is even. So if I add these together, 2n plus 2m minus 1 minus 1. I can remove the brackets. I don't need to change anything because I'm just adding them. So 2n plus 2m. The 2 negative ones would give me negative 2. What do you notice about all 3 terms? All 3 terms can be divided by 2. So if I factored out that 2, this is what I would be left with. I would be left with this number multiplied by 2. Since this number is a multiple of 2, it must be divisible by 2. That's how I do deductive reasoning. So what I want you to do is I actually want you to do all 4 questions. You've got a lot of time to work on during this class. Work with each other and go back to the class examples to see what makes sense. Follow through the instruction. You can replay the video and you can try your best to go through these 4 questions.